All right, so get this. We're going deep today into the world of meteorites.
Space rocks.
Yeah, exactly. Space rocks.
They're not just any rocks.
Right, they're not just any rocks. We're talking like time capsules.
From the early solar system.
Yeah, from the early solar system, holding all these secrets to like the formation of planets and maybe even the origins of life itself.
It's fascinating to think about, isn't it?
It is.
These objects have journeyed for millions of years,
right,
carrying with them a story written in their chemistry.
So we all know meteorites come from space, but like today we're going beyond the basics. We're getting into the nitty-gritty.
We're going deep.
Yeah, we're going deep. So think of it this way. You're at a cocktail party. Someone mentions meteorites.
Right.
And you're like,
boom.
Yeah, you drop some seriously cool knowledge about their actual chemistry.
No, that's how you become the life of the party.
That's how you do it.
So to do that, we're talking about the field of cosmochemistry.
Cosmochemistry. Okay, I'm intrigued. So is that like the ultimate cosmic detective work?
You could say that cosmochemistry is essentially the study of the chemistry of celestial objects.
Okay.
Including meteorites.
Gotcha.
It's like using a magnifying glass
right,
to analyze the elements and the minerals within these space rocks, and many of these formed in conditions that are drastically different from anything on Earth.
Oh, wow. Okay, so we're not just talking about like basic elements here, like iron or silicon, right?
Right.
There's got to be some crazy stuff in there.
Absolutely. Meteorites contain a mix of familiar and truly unique minerals, sometimes arranged in structures that we wouldn't see formed naturally here on Earth.
Wow.
A perfect example is the Widmanstätten pattern found in iron meteorites.
Widmanstätten pattern, that's a mouthful.
Yeah, it's a good one, though.
It is, but I've heard of those. They look almost like geoelectric artwork inside the metal.
Right. These patterns are formed by the intergrowth of iron-nickel alloys.
Okay.
And they tell us about the extremely slow cooling rates of ancient planetary cores, sometimes over millions of years.
Millions of years.
Yeah.
To cool down. That's wild.
Slow and steady.
Right.
Wins the race, I guess, in this case.
So are these iron meteorites basically chunks of ancient planetary cores?
That's one of the leading theories.
Really?
And just imagine holding a piece of a planet's heart in your hand.
Oh my God.
It's mind-boggling.
That is pretty wild. Okay, I'm officially hooked. But I know there are other types of meteorites too, right?
Right.
Not all of them are made of iron.
Right. Again, there are also stony meteorites, which are much more common.
Okay.
But still incredibly insightful.
So what makes them so special?
Well, stony meteorites are primarily composed of silicate minerals.
Okay.
And they're divided into two main groups, chondrites and achondrites.
Okay, I'm sensing there's a story here. So what's the difference between those two?
Well, chondrites are essentially the building blocks of planets.
Wow.
They're like time capsules from the early solar system made of tiny particles called chondrules. Chondrules. And these clump together billions of years ago.
Wow.
These guys have remained relatively unchanged since their formation, offering us a glimpse into the very beginnings of our solar system.
So they're like the raw ingredients before planets really got going.
Precisely.
Wow.
Now, chondrites are a bit different.
Okay.
They've been through the ringer, so to speak.
Okay.
They come from bodies like asteroids or even planets that have undergone melting and recrystallization.
So they're more like pieces of developed planets or asteroids.
Exactly.
Okay.
Chondrites offer clues about the processes that shaped these celestial bodies like volcanism or impacts.
Oh, wow.
Think of them as offering snapshots of planetary evolution.
All right, so chondrites are like the raw dough and chondrites are the baked cookies.
A delicious analogy.
I like it.
And both tell us fascinating stories about the history of our solar system.
That's amazing. Okay, but I have to ask, are there any meteorites that are, well, even more special than these?
You're reading my mind. There's one type in particular that gets scientists really excited, carbonaceous chondrites, and for a very specific reason.
All right, you've got my attention spill the cosmic tea. What makes them so unique?
Carbonaceous chondrites contain organic compounds.
Okay.
And not just any organic compounds. But the building blocks of life itself.
What? Amino acids? Wait, hold on. Amino acids in a rock. Isn't that what makes up proteins?
Yeah.
The stuff that builds our bodies?
You got it. And their presence in these meteorites suggests that the ingredients for life might have originated in space.
Wow.
And been delivered to Earth billions of years ago. It's a mind-blowing concept, isn't it?
It's crazy. So it's possible that life's starter kit came from a meteorite crashing to Earth.
That's one of the leading theories. It's called the exogenous delivery hypothesis.
Exogenous delivery hypothesis.
Yes.
Okay, I'm writing that down. Okay, so, but if these amino acids came from space, how do we know they're not just like contamination from Earth?
Right.
I mean, meteorites land here all the time.
Right.
Wouldn't they pick up stuff from our planet?
That's a great question, and scientists have been very careful to rule out contamination.
Okay.
They analyze the isotopes of the elements in these meteorites, looking for ratios that are distinct from anything found on Earth.
Isotopes, remind me, what are those again?
Isotopes are like variations of an element with the same number of protons but different numbers of neutrons.
Okay.
Think of it like this, they're the same element but with slightly different weights.
Gotcha.
By analyzing the ratios of these isotopes, scientists can determine whether the molecules originated on Earth or in space.
Ah, so they basically fingerprinted these amino acids and confirmed they're extraterrestrial.
Exactly, and the implications are huge. If the building blocks of life can form in space and be transported to planets, it opens up the possibility that life itself might not be unique to Earth.
Wow, that's a game changer. We're not just talking about the chemistry of rocks anymore.
Right.
We're talking about the possibility of life beyond Earth.
It's a truly humbling thought, and it's all thanks to the study of cosmochemistry.
Wow.
By analyzing the composition of these meteorites, we're piecing together a puzzle that connects us to the vastness of the universe and the potential for life beyond our planet.
So to bring it back to our cocktail party scenario, if someone starts talking about life on Mars, I can casually mention that we found the building blocks of life in meteorites.
Right.
Which could mean those same ingredients were delivered to other planets as well.
Exactly. You'd be dropping some serious knowledge bombs.
Oh, yeah.
And speaking of knowledge bombs,
Okay, let's hear it.
there's another fascinating aspect of carbonaceous chondrites that I think you'll find intriguing.
Okay, I'm all ears, hitting with it.
Remember those isotopes we talked about?
Uh-huh.
Well, by analyzing the isotopes of oxygen in these meteorites, scientists can actually trace their origin back to specific regions of the solar system.
So it's like a cosmic GPS built into the rock itself.
Precisely, they found that some of these carbonaceous chondrites likely originated in the outer solar system beyond the orbit of Jupiter.
Wow, that's incredible. But why is that so significant? Why does it matter where they came from?
Because it tells us about the movement of material throughout the early solar system.
Okay.
These meteorites could have brought water and other volatiles to the inner solar system,
Right.
possibly even playing a role in the formation of Earth's oceans.
Oh, wow. Okay, now we're talking about some serious cosmic connections. Like, these meteorites are messengers from the past,
Right.
carrying clues not only about the origins of life, but also about the formation of our planet and the solar system itself.
It's amazing, isn't it? And it all comes back to the study of chemistry.
Uh-huh.
By analyzing the composition of these space rocks, we're uncovering a story that spans billions of years and connects us to the very fabric of the universe.
It's truly mind-boggling, but I have to ask, what else can we learn from these meteorites? Is there anything else that scientists are particularly excited about?
There's always something new to discover. One area that's currently generating a lot of interest is the study of presolar grains.
Presolar grains, what are those?
These are tiny microscopic particles that formed around other stars before our solar system even existed.
Oh, wow.
They're like little stardust remnants captured within meteorites,
Okay.
offering a glimpse into the chemistry of the universe before our sun was even born.
Wow, so we're talking about materials that are literally older than our solar system.
Exactly, and by studying their composition, scientists can learn about the processes that occur in stars, the formation of elements, and even the evolution of galaxies. It's like having a window into the distant past of the universe, all thanks to these incredible space rocks.
Okay, my mind is officially blown. We've gone from the building blocks of life to the origins of our solar system to the chemistry of stars before our sun. It's incredible how much information is packed into these seemingly ordinary rocks.
It's truly remarkable, and we've only just scratched the surface of what we can learn from them. Each new meteorite that falls to Earth is a potential treasure trove of information waiting to be unlocked.
So if I understand correctly, we've got iron meteorites, which are like pieces of ancient planetary cores. Then we have stony meteorites, which come in two flavors. Chondrites, the raw ingredients of planets, and ichondrites, which are like pieces of evolved planets or asteroids. And then there are the rock stars of the meteorite world, carbonaceous chondrites, which contain amino acids, organic compounds, and even presolar grains.
That's a great summary, and each type of meteorite offers a unique window into the history and evolution of our solar system and the universe beyond.
It's also fascinating, but before we wrap up, I have one more question. What stands out to you as the most mind-blowing thing about meteorite chemistry? What's the one thing that really gets you excited about this field?
I think for me, it's the realization that these objects,
Right.
which seem so alien and foreign, actually hold the keys to understanding our own origins.
Right.
They bridge the gap between the vastness of space
Right.
and our place here on Earth.
I love that it's like that feeling you get when you look up at the night sky and realize just how interconnected everything is.
Exactly, and that sense of wonder,
Oh,
that
yeah.
drive to explore and understand
Right.
is what fuels scientific discovery. Who knows what other secrets are waiting to be unlocked in the next meteorite that falls to Earth?
Speaking of unlocking secrets, you mentioned earlier that scientists can determine the age of these meteorites. How do they actually do that? Is it like carbon dating?
It's a bit more complex than carbon dating,
Okay.
which is primarily used for dating organic materials.
Right.
For meteorites, we use a technique called radiometric dating.
Okay, break it down for me. How does radiometric dating work?
It's based on the decay of radioactive isotopes.
Okay,
You see, certain elements have unstable isotopes that decay over time into more stable forms.
right.
We know the rate at which this decay happens.
Uh-huh,
So by measuring the ratio of parent isotopes to daughter isotopes in a meteorite,
okay.
we can calculate how long it's been since it formed.
So it's like a cosmic clock ticking away inside these rocks.
Exactly. And some of these meteorites are incredibly old, dating back billions of years to the very beginnings of our solar system. It's incredible to hold a piece of material that's been around for that long.
It's like holding a piece of history, literally billions of years in the making, but it also makes you realize how young we are
Right.
in the grand scheme of things.
It's a humbling perspective, isn't it?
It is.
And it emphasizes the importance of studying these objects to piece together the puzzle of our cosmic origins.
You know, before we started this deep dive, I thought meteorites were just space rocks.
Yeah,
Interesting, sure, but just rocks. Now I see them as cosmic time capsules,
right.
filled with clues about the origins of life, the formation of planets, and the evolution of the universe.
I'm glad you see them that way now.
Yeah,
They truly are remarkable objects.
they are.
And we've only just begun to unravel their secrets.
Well, on that note, I think we've given our listeners plenty to ponder.
Absolutely.
If you're ever at a cocktail party and someone mentions meteorites, you'll now have some seriously fascinating facts to share.
Remember, these aren't just rocks. They're windows into the vastness of space and the interconnectedness of everything in the universe.
Beautiful put. So, to wrap up this deep dive, I'll leave you with one final thought. If meteorites brought the building blocks of life to Earth, what other secrets might they hold about the universe and our place in it? Keep looking up, keep asking questions, and who knows what incredible discoveries await.